Hello student, to the course of Physics of Linear and Nonlinear Optical Waveguides. Today we have lecture number 14, and in this lecture we are going to start the basic concept of material dispersion, which is very important in waveguide theory. So today we have lecture number 14. So let us recap what we have done, that beta in the last class, that the beta tilde has some restriction, that it should be less than n1 and greater than n2 for all guided rays. For all guided rays, inside a waveguide, these are the restriction of the beta. So, this is the fiber structure, and this is the parabolic index profile, and we find that the ray that is passing along the axis have the value of beta tilde maximum, which is equal to n1, and the ray that is moving like this, touching this point, the transit point, having an angle theta 0, for that beta tilde is minimum, and that value is equal to n2, where n2 is this one, n2 is this one, and n1 is this big value. So today we will going to understand another thing before going to the material dispersion part, that the relationship between beta tilde and beta. What is the relationship between beta tilde and beta? This is, by the way, is ray path constant and this is propagation constant. Where beta tilde do not have any kind of dimension, the propagation constant beta has dimension 1 by length, that you should always remember. Well, let me again draw this two dimensional plane where the ray is passing like this. So, when the ray is passing like this in this path from some point A to B, every point this theta is changing. So, at some point, say it is theta x, and as usual along this direction we have the refractive index, change of refractive index in x. So, beta tilde is in x cos of theta x, true always. Now, what is k, the propagation constant. K is in general is a vector quantity. It is mod of k and k unit vector is the direction along which the ray is propagating. The k is direction of that part, that direction, and mod of k is k 0 multiplied by the refractive index, because refractive index is changing every time. So, n should be a function of x. So, that is the, so this value is omega divided by c n x. What is kz? So, the z component of, so that means if the ray is passing like, if the ray is passing in this path, so this is the k vector we have. If I want to find out the component of the k vector along this direction, this is along z. So, this is kz component, and what is kz component? It is nothing but mod of k, then cos of theta function of x, which is by the way my beta. So, beta is a propagation constant along the direction of z, and k is a propagation constant. So, beta is a specific. So, it is the zth component of the propagation constant. So, beta here, so propagation constant is a component of the propagation constant, the component along the propagation direction. Z. Okay, so now I just put this value. So, my beta, which is the z component of the propagation vector k, is 2. So, here I should write the component. So, I should write clearly component of propagation vector. So, component, so here I should write it component of what? So, component of k along the propagation direction z. So, beta is k 0. So, let me erase this part. So, my beta is how much? K 0 n x cos theta x, that is all. Now, this n x cos theta x is my beta tilde. So, it is eventually k 0 multiplied by beta tilde. So, beta tilde is nothing but beta divided by k 0. So, the restriction we had last time is beta tilde for guided mode, beta tilde is less than n 1 greater than n 2 can be rewritten in terms of beta as a propagation constant, like N2 is less than beta divided by K0 is greater than N1. So, this is a very important restriction of all the guided for all the guided rays. This is an important restriction that we will going to explore more in our future classes. Okay, after that we will directly jump to one of the major property of waveguide, which is called the material dispersion. Material dispersion. So, quickly we brush up the concept of material dispersion. So, different wavelength is nothing but the different wavelength propagates at different group velocities. So, different wavelength propagate at different So, that happens because n is a function of lambda. So, that is the main issue here. So, the refractive index n is a function of lambda. So, that is the reason due to which the wave are having lambda 1 and the wave is having lambda 2 has two different group velocities. So, that we are going to explore in a more detailed manner, but before that we need to find out how n is a function of lambda, what is the functional form, and in order to do that we going to use or going to refresh the Lorentz model for dielectrics. So, Lorentz model for the dielectrics we try to understand. This is not a very new thing, but still I feel that it will be useful for you to understand the concept of dispersion. In a dielectric, if I launch an varying electric field like this is the varying electric field. Electric field I can write as E0 e to the power of I omega t. So, some frequency omega, the electric field is launched having some frequency omega. So, what happened in the dielectrics? This dipole will going to oscillate under the varying oscillating external electric field. So, there should be a dipole oscillation. Now, we know what is the polarization, because the refractive index is a consequence of the polarization of the system, especially for dielectric systems. So, polarization P in vectorial form, if I write, it is this quantity. If I consider only the linear part of that linear polarization, then this is the expression. Obviously, for nonlinear cases there will be higher order term. So, we are not going to the nonlinear domain right now. For linear case, P is simply epsilon 0 chi 1 E. Now, the equation of motion, if I want to find out what is the equation of motion of this system. So, the equation of motion is m double dot is equal to the total force. Now, what is the total force? So, the total force experienced by this tiny dipole is like that. F total is a combination of the three term Fe, Fd and Fr. What is Fe? Fe is the driving term due to the external electric field. What is Fd? Fd is minus of gamma x r, this is a velocity dependent term, and this is basically the damping term. It's a damping force actually. So, the Fe is the driving force or driving term, Fd is a damping force, and Fr, which is minus of, because we are considering that is a spring mass, like a spring mass system, dipole is oscillating, it is kx is a restoring force. All these things are well known, so I do not need to explain much. I just need to extract the expression of the refractive index out of this model, and then it will be readily evident that how the refractive index is a function of lambda. That is all. That is the goal of this treatment. So, I just put the values like this, and then x double dot is equal to okay. So, let me write few steps, then I am going to calculate that. So, x double dot plus gamma divided by m x dot plus k divided by m x is equal to the driving term E e. Mind it, k here is a spring constant, not the propagation constant. These are different things. So, maybe the notation looks same, but the k is the spring constant, usual coming usually from the Hooke's law. Now, I defined gamma divided by m is the damping term as big gamma, and k divided by m with our usual omega square, which is the resonance frequency of the system, that we know that in a spring mass system the resonance frequency is nothing but root over of km, that I am just using that one. So, my differential equation becomes simply d2x dt square plus gamma dx dt plus omega 0 square x is E. Okay, when I divide, it should be E divided by m, E m E. So, this is the differential equation. Now, I need to solve. So, this differential equation is nothing but the force damped oscillation expression, a very well known differential equation, nothing special here. And we know how to solve this. So, the solution I want in this form. So, solution, the solution I should have in this particular form, e to the power I of omega t, because the electric field, against the electric field which is E external electric field, the x will also follow the same vibration frequency, and I am expecting the solution in this form. Once I have this solution in this, assume that the solution in this form, I can readily calculate my x 0, just putting this solution here in this equation, putting this solution in this equation, I can readily find out my x 0 as E divided by m E as usual, divided by, now I put this value here. So, double derivative, when I make a double derivative, there should be a minus of omega square. So, and omega square is already here. So, it should be simply omega square minus omega square plus I gamma omega, and it should be E 0 because I am calculating x. So, from this expression I can calculate the dipole moment. The dipole moment is simply P, the dipole moment is simply charge multiplied by the distance x. So, here it should be P equal to E square divided by m, then E whole divided by that quantity omega square minus omega square, omega 0 square minus omega square I gamma omega. Polarization, if I want to calculate, because I started with the expression of the polarization, because the refractive index, the information of refractive index is hidden here. So, I need to extract that, this portion I need to extract that. So, the polarization is P, which I can write dipole moment, and n is a number of dipole per unit volume. So, dipole moment per unit volume is my polarization. So, n here is the number of dipole per unit volume. So, I can write my P in terms of small p n, and my small p already I calculate. So, it is, the expression is simply n E square divided by m, then E divided by omega 0 square minus omega square plus I gamma omega, which is basically epsilon 0 chi 1 E. So, now comparing these two expression, I can extract the value of chi 1. My chi 1 susceptibility, first order susceptibility is E square n divided by m epsilon 0. I just divide this epsilon 0 and then compare that whole divided by whatever the term I already have, omega naught square minus omega square plus I gamma omega. Now, my n square, which readily become function of omega because it is related to chi as 1 plus chi I. Chi I can find this is a function of omega. So, through chi 1 I can have the value of n square which becomes a function of omega. So, I can again this quantity is nothing but the relative susceptibility. Relative permittivity. So, now I have 1 plus E n divided by m epsilon whole divided by omega 0 minus omega square plus I gamma omega. This quantity normally written in a more compact form. So, let me write it the compact form in terms of plasma frequency. So, this is like this. The constant okay, I think I am missing one E square here. So, this is E square and then m epsilon 0. This is a plasma frequency term. Well, n of omega, I can now find one interesting thing, that n square omega is complex, and if I just remove, try to write it as standard form a plus I v x plus I y form or a plus I b form. So, here I think I should have a negative sign. And the denominator I have multiply the numerator and denominator by omega 0 square minus omega square minus I gamma omega. Then this will have term like 1 plus omega p omega 0 square minus omega square. This is the real part I am extracting out, and the denominator it should be simply omega 0 square, here I should have a square, minus omega square whole square, then plus of gamma square omega square, and then minus of I omega p gamma of omega all divided by omega 0 minus omega square whole square plus gamma square omega square. So, this is a part containing the complex term, and this term is basically due to gives us a loss. The refractive index, if I have a complex term, it gives us a loss. So, the refractive index contribution is coming through the first term, that is interesting, and that I need to just mention. So, now this gamma is lost. So, if I neglect the loss, and I can neglect that when the frequency is far away from the resonance frequency of the systems. So, in that case, now neglecting, sorry, gamma, so which is far, frequency is far away from the resonance frequency, then I can write n square omega as 1 plus omega p square divided by omega 0 square minus omega square. Okay, so this is roughly the expression, and from here we can readily see that how the refractive index is a function of omega, but that is not the end. In general, what happened, differently situated electrons within a given molecule experiences different resonance. Resonance frequencies, because all the in this calculation we consider the resonance frequency for all the electrons is same, which is not true. So, I need to consider that as well. So, n omega should be written in this particular form. For every, the resonance frequency is now different for different differently situated electrons. So, I need to take account that as well by putting this summation sign. So, for different I have different resonance frequency, and then I can have an expression. If I now write this expression in terms of lambda, I have something like this, some constant, say ai lambda square divided by lambda square minus lambda I square, using the expression of the relationship between omega and lambda. This equation is basically called the Selmar equation. Selmar equation. So, Selmar equation is the equation through which you can understand how the refractive index will going to vary with respect to lambda. So, with this note I would like to conclude, because today we do not have much time. In the next class we will go on with this concept. So, now from today's class we understand that the refractive index is a function of lambda, and that is why when we launch a light with different frequency component, it will pass through the system with a different velocity, group velocity, because n is changing as a function of lambda, and that is why there is a time lag between these two component, frequency component of the wave, and eventually we have the dispersion. So, we will discuss these things, and also like to learn how, because of the dispersion, there is a broadening of of a optical pulse. So, let us do in the next class all this calculation. So, thank you for your attention and see you in the next class.